Now we're good. Thank you.
In the interim. Can you just check it's recording? You can see a little red.
Yeah, it says
rec. Thank you. Okay, we're underway. So, starting to get a little bit more serious this week after last week's sort of gentle warm-up. Most things are in place at this point. I had more than usual difficulty with mastering physics. It seems like it's changed a little bit since the fall. And the publisher was not super helpful. But recitations begin today and tomorrow. Hopefully you're all signed up for a 1604 recitation section. If you are not, please do so immediately. So they will begin today, tomorrow. Turns out, by good fortune, we have the same two recitation PAs, namely Ben and Reese. I can't quite remember who's doing which, but anyway. So they're going to start today. I will have Ben and Reese, in a rather sort of relaxed way, work through maybe a couple of introductory thermodynamics problems with you. Office hours as scheduled. Some of you have recently joined the course, so weren't in the first semester. I'm not going to ask here in class because I've been interacting with a few of you online, but if any of you have issues gaining access to mastering physics still, see me after class so we can try and get those straightened out as quickly as possible. I finally did get things in place enough that I could post the first problem set, just because it's a little bit later than in the usual cycle. I pushed this back to an unusual due date, so this first problem set has a due date of midnight on Saturday. 10 problems shouldn't be too challenging, sort of introductory thermo stuff we covered last week and we'll cover today. And then once we've gotten through this week, we'll revert to the usual cycle of Thursday midnight for due dates for resets. Practice problem sets are appearing. They're up already for chapters 17 and 18 material from the publisher. Something there also seems to have changed since the fall in that there are more problems with practice presets. I assume that's a good thing. Of course, you don't have to do all of them, but if you're feeling like you want to exercise yourself on the topics that are appearing in the sort of simultaneous graded presets, that's a good place to start getting some practice. So please make use of those as you see fit. Piazza didn't really take off much last fall. I'm still sort of keen to have that as a resource, and we'll see if I can find ways to make it more useful for you and more attractive for you to sort of interact with each other. So, last thing which I forgot to put on there. So my lecture notes are posted. Something else having a little bit of technical difficulty with is posting the videos. Turns out YouTube doesn't allow you more than a very small number of channels, which I didn't know until yesterday. So I just need to play around with that, and once I've done that, hopefully the videos will be appearing online as well. Okay, let me pause. Hopefully at this point there won't be too many more introductory comments of this nature, but let me just pause and ask for questions or comments before we jump into thermodynamics. Okay, last thing as it crosses my mind, a few of you did a makeup final yesterday. I haven't heard from the Center for Student Advising anything about that yet, but presumably I'll get the scripts pretty soon. They'll be graded as soon as possible, and then just to round out from the fall semester, those of you who are in the course in the fall semester, I know some of you are still waiting for feedback from me on questions about the final and grades. I have not forgotten. I just want to take care of it all in one shot, which will likely be this weekend. All right, so let's get back to business. Thermodynamics. So we're going to still be talking from a somewhat macroscopic perspective today. So I'll try and touch on the microscopic features where it's helpful and relevant. And then on Thursday, we're going to turn our attention pretty much primarily to the microscopic picture and look at the atomic level in sort of ideal gases and see what we can learn about them and how that informs the macroscopic behaviors that we've been exploring. So for today, we'll start off talking about heat transfer, thermal energy transfer, what the implications and manifestations of that are. First off, if we are dealing with some material that remains within a particular phase, by that I mean either solid, liquid, or gas. And then the second possibility is that as we input or extract thermal energy, that the phase of the material actually changes. So we're going to look at both of these things, tie them together, maybe do a working example. And then we're going to go back, having already seen some of the phenomena or different types of mechanisms for transferring thermal energy. We're going to go back and look at two of the three mechanisms we talked about, namely conduction and radiation, and be somewhat more quantitative, see what we can say about parameterizing those processes. When we talk about radiation, I'll take a little bit of a detour just to tell you for a few minutes about a particular characterization of radiation from so-called black bodies, objects that are in thermal equilibrium with their surroundings. We already have an idea what that means. And in particular, these black body radiators, well, there are many examples of close to ideal black bodies in our daily world, close approximations to it. And then there are examples in much different contexts where black body radiation spectra are relevant, and the one I'm going to take the detour into telling you a little bit about is the black body radiation spectrum of the universe as a whole, namely the cosmic microwave background radiation. And then if there's time, we'll come back and revisit the ideal gas equation that we introduced on Thursday, and add a little bit more realism, which is to say we will relax the requirement that those molecules in our ideal gas approximation are non-interacting. We'll start to see what happens when we take into account the fact that there's some level of interaction and that they're not just microscopic sort of billiard balls in the ideal picture. So that should get us through today. Hopefully I'll manage most of it. So, let's see, where do I want to jump in? Okay, thermal energy transfer. I also have to figure out how to better use the chalkboards. Not so easy with this geometry, because the ones behind here are tall and skinny, which is not very nice to write on. So I'm actually going to stay with down here for today and see how that works. All right, so thermal energy transfer. You'll see that I'm kind of downplaying the word heat, a sort of historical word. We now know, have done for a long time, that heat is just thermal energy. Quite what that is we'll better understand on Thursday, but I'm pretty much avoiding saying heat for the most part, except where it's historically relevant. So what are we talking about? We're basically talking about energy transfer and to good approximation, though not always, we're talking about energy transfer from what we call warmer to cooler objects, systems, arising solely from the fact that there's a temperature difference between them. A little bit of a imprecise statement, but it's fine for us for right now. One thing we want to do right off the bat is define what this thermal energy is. We're going to give it a symbol, a name, if you will. And so we tend to give it the symbol capital Q for thermal energy. And a convention, which is the source of some confusion between the physics and chemistry communities, is that Q is positive when energy, let's see, how do I want to say this, is transferred into an object or a medium. And by contrast, of course, Q is negative when the energy is transferred out of. Okay, so keep that convention in mind. Of course, it's just a convention. Just we want to be consistent. And again, it's kind of annoying. I believe this sort of difference in convention between the physics and chemistry communities is still persistent. It's not going to go away anytime soon. So just keep in mind that that is our definition in physics world. So, just to drive this home a little bit, let's say I have symbolically some sort of system. I'm just going to represent by this hashed rectangle. And let's say this system is in equilibrium itself, thermal equilibrium itself, which is to say it has a common temperature everywhere. And it's in an outside environment, which also is assumed to be in thermal equilibrium, so at its own certain temperature. So the temperature of a system embedded in some external environment, which is at its own temperature. And so in the case that the temperature of the system is greater than the temperature of the environment, so this is hotter than the environment it finds itself in, what you would expect is that thermal energy is transferred from the warmer to the cooler object, or warmer to cooler material, so we're going to note this by Q. And so in this sense, if I'm focusing on the system, I would say that the Q is less than 0. Okay, so I'm focusing on the system. This is losing thermal energy. It's going into the environment, which is cooler than the system itself. So Q in this case refers to the thermal energy associated with the system. It's going out, so it's got a negative sign. Okay? I don't think I'm even going to take the time to reverse this. Maybe I'll just do it on the fly. Don't be nervous about what I'm doing here. I know it's not the nicest thing for you to do when you're taking notes. But let's just imagine I turn everything around here. So I'm going to make the system now not warmer than its environment, but cooler. And so in this case, what you would expect is that there's thermal energy coming into my system. And in that sense, since Q is referring to the system here, I've got a positive thermal energy transfer into that system or that object. Okay? So again, don't get confused by the fact that I quickly overwrote that with two scenarios. It's just a simple convention that we're going to need to make sure we follow. All right, I'm not going to say much at all about different units of thermal energy. As you well know, we have adopted the SI convention for energy units for the most part, named joules. Historically, there are plenty of other types of units associated with heat before it really became associated with thermal energy. So you will hear, for example, of calories. We still hear about that in the context of food science in particular. You'll hear other weird things. The only place I hear the following unit these days is in the context of air conditioners, but you'll hear, for example, of a British thermal unit, BTU. All sorts of different historical units. We're going to use joules for the most part. If you ever need to do a conversion, you'll obviously have a conversion factor. Straightforward. So let's stick with joules to keep our life simple and metric. All right. So, with that said, let's turn our attention to the two cases that I outlined on the chalkboard on the right side. We want to look at how we can characterize thermal energy transfer of a material when it's staying in the same phase initially, and then we're going to turn our attention to the case where it changes phase. Okay, so let's start off with the case where it remains in a single phase. I'm going to erase this, I think. Hopefully you guys have got all of that. In the spirit of trying to figure out how to make good use of the chalkboard here, I'm going to try and keep this consistently on the right side. All right, so we're going to start off talking about staying within one phase. Within a phase or state, it's the same thing. Okay, so what we experience by doing experiments is if we take a bunch of different materials and we put them in some sort of standardized environment, and maybe we start to add thermal energy to them. Empirically, what we find is that the response, measured in terms of the temperature of the material or the temperature of the object, depends, maybe not surprisingly, on what the object is made of. Okay? And of course, it's going to depend on how much of it. So what we see empirically or experimentally is simple material-dependent behaviors. So for example, let me give you a couple of schematic representations of this. First off, what I'm going to plot is on the horizontal axis, thermal energy input, Q, measured in joules. And then on the vertical axis, I'm going to characterize the change in temperature of the material. It doesn't matter what the units are. Let me put it in Kelvin, just for argument's sake. All right, so put in a certain amount of thermal energy. If I'm adding thermal energy, but we don't really have a full understanding of this yet, we will do by Thursday. What we expect to happen if I add thermal energy to some material is its temperature is going to increase. Okay? And empirically, what we find, at least within a phase, to some approximation, is that the relationship between the temperature change and the amount of thermal energy input is linear. Okay? So for example, I might see something that looks like this over some range of energy inputs, some range of delta T's. So this might be material 1, substance 1. And then I can take some other material, do the same set of measurements, and we're going to find, again, with some idealizations, a second set of parameters, maybe something that looks like this. So 2 materials, material 1, material 2. Okay, so first off, to some approximation, again, idealization, we find the observation that delta T is proportional to the amount of energy input into the amount of material that we have. Okay? So as soon as we have a proportionality like that, we know what our next step is likely to be. And so the way we're going to do this is put in a constant of proportionality. And typically this is done in the following way. So let me write this as Q equals C delta T, something like this. This is a constant, obviously, and it's what's called the heat capacity. Now, you'll see I haven't so far got any explicit mention of the amount of material in here. This is just for a fixed amount of material. It's showing the constant of proportionality. I'm going to normalize it to the amount of material in just a moment. But for now, let's just take a look at this and the 2 different materials. So let's take a look, for example, at this point, a certain amount of thermal energy that I input. In the case of material 1, I read off this temperature change. In the case of material 2, I read off this temperature change. So obviously we're getting different responses here. These materials have different heat capacities. They have different responses in terms of their temperature change as we add or possibly conversely extract thermal energy. No big deal. Okay. So this is the first observation that approximately speaking, we've got this linear relationship like this that allows us to define a constant of proportionality, namely heat capacity. All right. So what I really maybe am more interested in doing is folding in not just some dependence on the material in question, but how much of it we have. As you might expect, the more material we have for a given thermal energy input, the less the temperature change is going to be, because it's presumably distributed over more of the material. So we'd like to fold in how much material we have as well into this. And so if we do that, we can actually write this in the following way. So let me write this here, or including explicitly the mass dependence, the amount of stuff dependence. I can write this as the following. So I'm going to write this now as Q equals, and this is sort of slightly annoying notation, but let me just write it down and then briefly talk about it. Okay, so all I've done here is replace what was supposed to be a capital C, so maybe not obvious from the way I wrote it, but this is supposed to be a capital C. What I've replaced it with is another constant, lowercase c, and the amount of material, the mass. And so when I do this, when I extract the mass from here, because if you think about it, it's presumably implicitly embedded in it. If I extract it, what I get out of here is a different constant, just removing the mass. And this is what tends to be called the specific heat mass. Okay? So, I'm going to downplay this first one, kind of not so useful because it kind of hides the fact that the mass is a factor in here. Let's pull it out explicitly and write it in this form. So now I've got the amount of material, a specific heat capacity for the material, and the same intrinsic physical behavior. Okay? So this is going to be our first useful equation when it comes to doing calculations or predicting the response of certain materials to thermal energy. Pretty straightforward. We'll do in a few moments maybe a calculation with it, but add thermal energy, temperature is going to increase. Depends on the amount of the material, and then of course it depends on some material specific quantity. And we'll talk a little bit more about that as we get into things. Okay, so let's see. Give you a sense of scales of units here. I don't think I'm going to write this up on the chalkboard. I'll just talk about it for a moment. It's in my notes if any of you want to check the numbers. Just to give you a sense of scale. How much thermal energy do we need to change the temperature of a typical human body by, let's say, 2 degrees, whether it's Celsius or Kelvin, agnostic there, same unit in terms of size, obviously. How much thermal energy do we need to input to raise the temperature of an average human body by 2 degrees? Why did I choose those particular numbers? Well, human body, we all know those pretty well. A 2-degree temperature rise. Occasionally, if you are sick, you have a fever, you take your body temperature, of course, you know if you have a fever, your body temperature is elevated. 2 degrees on either the Kelvin or Celsius scale is quite a significant increase in temperature for a human body, but not totally out of the realm of possibility. So, let's say you've got a fever, your body temperature goes up by 2 Celsius. Let's say you've got an average, maybe slightly more than average human who weighs 80 kilos. If you do a quick calculation, assuming that the person is primarily or dominantly made up of water, maybe we should just write down what the number for water is for that specific heat capacity. So for water, C, it turns out, is approximately 4.2 times 10 to the 3. The units you can easily figure out. I didn't explicitly describe them, but you can easily figure out what they are. It's about 4 times 10 to the 3 joules per kilogram Celsius. All right, so actually has an unusually high specific heat capacity. Water is very anomalous when it comes to physical parameters and thermodynamic parameters. All right, if you could plug in here, delta T of 2 Celsius, 80 kilos, this specific heat capacity, assuming humans are primarily water, the amount of thermal energy that you will kick out of this calculation is actually close to 700,000 joules, okay? Just to give you a sense of scale. So that's how much thermal energy somehow you would need to have input into the human body if its temperature on average has risen by a couple of Celsius. Yes?
Is that 4.2 or 42?
4.2, though you can't quite see the point. There you go. So, about 700,000 joules needed to raise your body temperature by 2 Celsius, 2 Kelvin. That sounds like a lot, it's just the way we define joules. Just as an amusing FYI, that's about the amount of energy you could extract from maybe a handful of sugar cubes. So maybe, I don't know, 20 or 30 sugar cubes, just grab a handful of them. That's the amount of energy you could extract from those. So always ballpark things good to know here. All right, pretty simple, okay? All we are going to need to do in these cases is relate thermal energy input or output, temperature change, so long as we know the specific heat capacity of the material. All right, so let's see, anything else I want to say about this at present? No, I think that's it. Just pause, make sure you're okay with this. And then we're going to talk about the second scenario where we actually see a phase change as we add or take away thermal energy. Okay, all right, so let's do that over on this chalkboard. So we've already talked a little bit about state or phase changes. Most materials can exist in one of three phases: solid, liquid, gas. So those are the phases that we're talking about. So, thermal energy transfer. Changing phase. So inevitably, if we continue adding or taking out thermal energy, we're going to get to a point where we reach the temperature where we expect the phase of some material to change. So we need to characterize that. And what we can say, a few things generically to begin with. So phase change and the expressed kind of like this. Of course, in general, we expect to go solid, liquid, gas, and background here if we wish. It's a little unusual and not completely unknown for materials to go between the solid and gas phase directly. So in principle, I want to make this triangle complete. So we're talking about just phase changes as we go around here. So what do we find typically? Phase changes occur at constant temperature values for whatever the material is. So that we can certainly say. And then what we typically are observing as this happens are a couple of things. First off, we're going to see usually a change in volume or density, possibly a change in order, which really means at the microscopic level how the atoms or molecules are arranged. And of course, what we are definitely always seeing is the absorption or emission of thermal energy. So those are generic characteristics of a phase transition in some material. Let me just give you a quick example of what to expect if I was showing you for a volume or mass of water. Let's see what we can look at here in terms of temperature. So this is for water. And what I want to try and characterize here is a constant, let's say, addition of thermal energy. So let me just call this a, let me just say it's Q as a function of time. So it's Q constant rate of input of added energy. Okay, it's not exactly precise, but it doesn't matter. What I'm trying to say is, how does this look like if I take first off a certain amount of ice, and let's put on the Celsius scale, maybe let's put 0 Celsius here, maybe I'll put 100 Celsius here at atmospheric pressure. These, as we know, are defined to be the melting and boiling points of water. So if I start off with a chunk of ice, and it's at a temperature that's below 0 Celsius, what I would expect to happen is, as I start off adding thermal energy, the temperature of that volume of ice is going to gradually increase. We're assuming a linear dependence. Once it hits this temperature where we know it's undergoing a phase transition from solid to liquid, what we expect to happen is as we continue to add thermal energy, the phase transition is occurring, but the temperature of the whole system does not change. Okay? important characteristic of the phase transfer. The temperature doesn't change while it's happening. Once the material has fully melted, so now we have an equivalent mass to the water, what we expect now is the temperature of that water to increase. And what I'm trying to exaggerate by the way I'm about to draw this is that the slope there doesn't necessarily have to be the same as the slope of the ice phase in terms of specific heat capacity. In fact, in general, they'll be different. So you see the slope here and here differ. And then I hit my other phase change temperature.